How do the laboratory synthesis conditions, such as hydrothermal reaction at 120 degrees Celsius, influence the crystallinity, morphology, and ultimately the electrochemical characteristics of natriumpO4CO3, and what might be the reasons behind the material's high initial charging capacity of 200 mA Hu? G superscript 1 followed by a rapid decay to around 100 mA H G superscript 1 after just 10 cycles. How can insights drawn from both the charge/discharge curves of Na2Fe-PO4F and Na2Fe/2Mn/2 PO4F and the performance trends observed in natriumpO4CO3 guide further research toward optimizing cathode materials for sodium-ion batteries? And what additional studies could be conducted to address issues such as capacity fading and structural stability in these promising materials? Can Davis Zurns manufacture solid-state sodium-ion batteries made from seawater in Latvia? How do the diverse types and forms of polyanionic compounds open up new avenues for designing cathode materials for sodium-ion batteries compared to traditional layered oxides? And in what ways do the multiple transition metal elements that these compounds can incorporate influence their redox behavior and overall electrochemical performance? How does the capability to combine various anionic groups within a single polyanionic framework expand the range of structural configurations? And what impact does this have on the material properties such as ionic conductivity and stability during battery operation? How does the high anion electronegativity in these compounds contribute to achieving a higher working voltage when used as cathode materials, and what are the underlying electronic mechanisms, such as the inductive effect, that modulate the voltage output? Given that these materials offer high voltage, what factors are responsible for the relatively poor reversibility observed in polyanionic compounds compared to metal oxide cathodes? And how might the intrinsic structural characteristics contribute to this limitation? How can researchers utilize the vast combination possibilities afforded by the very transition metals and anionic groups to address challenges in reversibility while maintaining or enhancing the high voltage performance? How might advanced synthesis methods, material engineering, or defect management strategies be employed to optimize the trade-off between high working voltage and cycle reversibility in these sodium-ion battery cathodes? In what ways does the extensive variety of combinations in polyanionic compounds provide new research ideas or strategies for tailoring cathode materials, and how can these insights be applied to overcome current performance limitations? What experimental techniques or computational models could be devised to further investigate and fine-tune the interplay between anionic electronegativity, structural diversity, and transition metal selection in order to develop next-generation cathode materials that balance high voltage performance with improved reversibility? What?